questions about topics, about sessions, about homework? Yes, Irene?
I was thinking when I was doing some of the tasks this week, I've been using my IDE because I'm actually a returner, so a 4-year career break, rather than doing it in LeetCode directly. And then I copy it from my IDE to LeetCode. In interview situations, can you do that? Because if I'm interviewing someone, I want to see how they're going to operate in a real working, authentic environment. And they're not going to be on a LeetCode editor. I just wondered if there was any.
Yeah, let me start then, Lilia, for sure. Actually, I was working for Revolut for 3 years, and we didn't have LeetCode similar problems for the first ever interview. We had a bit different, but it was all about working an IntelliJ IDEA and see how people use Java, how they use it. Like it was kind of, okay, here is a product owner, they give you a task, what you're going to do next. So like seeing work-related experience. So I would say every company have a bit different approach to doing an interview. And in case of Revolut, yes, I would encourage you to use your IDE to see how you would solve it, like during your working day, like basically real-time problem, but how do you do it as normal problem in your real life? Yeah.
Okay.
Lilia, please add to this.
Yeah, so it's very depend on the company, and usually in the invitation, you will it will be at the first step when you will talk with HR will tell you whether it will be in the year of your choice, because you need to upfront to prepare it. If it if there will be invitation with the link on the whiteboard, kind of whiteboard, they don't use for coding. It is code. A different platform where you're writing your code without a compilation editor, the similar like LeetCode. Yeah, so it's very depends on the company, but you will know it's upfront.
Okay, thank you. I was just going to maybe even suggest an interview to say, is it possible to use my ID and then just copy it into LeetCode? Because they can view you can share your ID as well with them. I've been in the industry for a long time, but I've never actually done a LeetCode interview because it's a newer thing. So I just wondered. Okay.
Yeah, usually if it's very LeetCode and when they not scan the syntaxes of language, because some companies very agnostic to the engineers who is they hired. At this you should expect that it will be a kind of LeetCode platform where you will write code and yeah.
Yeah, for example, HackerRank, some companies do exactly the HackerRank contest with you in real time, and you just write your code in HackerRank platform, which is good because you have syntax sugar, all these highlights, and yes, that HackerRank could be used for this as well.
Okay, thank you, ladies. Thanks.
Any more? And I count from 10 to 0 to see if there are any. Okay. Eloy?
Yeah, hello. Irina, I have a question about the challenge we did this week, because I'm new to HackerRank and I never did challenges before. So I realized that it's a timed thing. So does it mean that I will not be able to do one of the tasks I didn't complete, like later today or tomorrow?
I didn't mean it. So you could complete them later.
Oh,
yes. Why we limited this time? Because we do leadership board for those who completed it by timing. Yeah, so we also announce those people. But if you want to complete them later, you can complete all contests later.
Okay, fantastic. Thank you very much.
Good. Okay, any more? I count from 5 to 0. 5, 4, 3, 2, 1, Zero, no questions. Now we can go to the content of our lecture.
Okay, just 1 second, we'll share my screen. So I have shared a link to the whiteboard already. So this is our new challenge week. I will briefly explain what we are going to cover today. So today we will start with introduction to tree. So tree we will explore how traverse tree. There is basically two approach how we are going to traverse. One of them required to know recursion. So this is like all the three questions can be solved with iterative way, but as a recursion one. But it is kind of foundation of the tree. And next, it will recursion, if you will understand quite nicely, because I emphasize a lot in this class on the small recursion problem, because next recursion will be applied for dynamic programming and for graph questions as well. So it's nice to understand and to be comfortable with recursion itself. But along with recursion, you can always solve them in an iterative way. Yeah, so today we will cover foundation of the tree, how we're going to traverse them. We'll emphasize a lot on recursion. By the next week, I would expect from you folks, because it will be connected, the next week will be connected with this week. Next week, I'm going to cover more advanced questions on the tree. That's why this week more focus on the foundation problem. And all these 4 questions, they very very light if you understand the material of the lecture today. So, but it's nice just to practice and practice and be comfortable with those kind of questions. Next week we will cover a more advanced tree problem, and also we will explore another type of tree like trie. So yeah, basically that's it. If you have any questions now, if you don't, I will move to the lecture. Okay, let's go. So introduction to tree. Tree is again, it is a data structure. It's the same data structure like we have linked list data structure, we have array list data structure. So this is our new data structure, a tree. Composed of nodes, where each node connects to one and more child nodes. Each node in the tree contains the data it stores and reference to its child nodes. The most common type of tree is binary tree, in which each node connects to up to 2 children, left child and right child. So this is example of the tree, how it looks like. This is a code. How we represent the tree node. This is the representation just of the node. This one, it is our node. Folks, do you remember last time I also show you how we represent a linked list node? And so basically this is another data structure and have also representation of node. In this case, we have also value, the same like for linked list, but for linked list, we had a reference to the next node. In this case, we have reference for 2 nodes because it's usually left or right, but sometimes it could be just one child as well. So, terminology. We have parent, we have age, and we have child node. Parent node with 1 or more child. This one our parent node. This our child nodes. This our ages, which is how we connect with child nodes. So move on. We have another terminologies which is related to tree. It's depth, path, and height. So in this case, depth will be this one, the number of edges from the root to a given node. So for example, the depth of this one will be 1. Here will be 0. And if we're talking about depth here, so it will be a depth of 2. So basically this, how it is. Path, a single continuous sequence of nodes connected by the edge. This is our path in the tree. And high. High could be this one or this one. So it is the length of the longest path from the root to leaf. So if we will add here another node, make it like this. So then here it will be our high because we take the longest one. So yeah, I think the path high. Yeah, questions, please.
Hi, Lilia. I'm
Hi.
back.
Welcome back.
I have one quick question. What's the difference between a heap and a tree? Because in heap, we don't represent that as a node, right?
Say again?
In heap, we don't represent the elements of the heap as a node.
What is the difference between heap
and tree?
Heap and tree. Under heap, you're using the tree representation. So there is no difference. Just how you arrange it. The one thing under heap, you are using the special tree, which is after balance. And so, yeah, I cover it.
Yeah, I covered it last week. I caught up. Yeah. My question is, here in the tree, instead of the actual node, we are talking about pointers, right? Like a linked list, no?
No. They both using tree. I mean, this is the data structure tree. It is tree could be different ways. When we were talking about heap, there we were using a very specific tree underneath, which is included different specific characteristic on which we can rely. And we've wrapped it into a heap. But we know that underneath it is used heap, and it is self-balance. So for example, there can be this case when we have tree. So couldn't be, this is also tree. But once it is tree, we can say that it is actually a linked list as well. So this is kind of nuances, which is you will pick up and you will start to understand. This class particular, we are covering currently just the foundation of the tree. But there is a very wide different type of the tree, which is a binary search tree, binary tree, self-balance tree. Then we can go even deeper, like red-black tree. So they have kind of different configurations.
Yeah.
That's what makes them. When we were talking about heap, I just explained it, what kind of, that this actually data structure has underneath tree, which is the binary tree and self-balance tree. So I put emphasis just to explain what is time complexity for different operation on the heap came from. Okay. But it is tree. Today we are covering tree, but currently we are the most basic tree covering, binary tree.
Okay. So you are saying that heap is also a type of tree, right?
Yes.
Okay, thank you.
Yeah. Okay. Today we are covering, we'll focus on the binary tree. This is the terminologies which you need to know. Don't be confused with the other different type of tree now. Just telling how it can looks like. That there could be nodes in different order with different values. We are not emphasizing on it. The goal of this lecture today, just to know what is the tree. The most terminology like parent, child nodes, ages. Very important to know what is depth of path and height, because quite frequently we have LeetCode task where we are required to find path, depth, or path. Now we will cover the most important things, like how we're going to traverse tree. There is two types of traverse. It's depth first search and it is breadth first search. The same traverse things we will use for graph. After 2 weeks, we will start covering graphs. So, and we will and you will see that they are also crossing each other, tree and graphs. So let's. This was one important thing which is I wanted to cover, but I somewhere I put it. This one, ages. So yeah, we have ages between two nodes. Tree usually have direct ages, meaning the age only point from parent to child. This is also very important to understand, that we are traversing from the parent to the child directly. Because when we will start covering graphs, you will see that it could be a direct or indirect graph. That's why it's important to understand probably today, because I'm sure in the graph topics we will also cover what is direct and indirect, but tree can be only direct, has only direct ages, means from the parent to the child connection. Okay, now tree traversal. We have depth first search. Is a method of exploring all nodes of the tree by starting at the root and moving as far down as branch as possible before backtracking to explore other branches. So what does it mean? This is the example, our tree. We're starting moving to 2, then from 2 we are moving to 1. This is our leaf node or child node. So now we are backtracking back. This is calling backtracking. So we reached to the point where there is no other nodes. We are backtracking back, and then we are going to 3, and from 3 we're going to 2, and from 2 we're going to 4, and from 4 we're going to 5, 6, and then back. That's how the first search working. With some tweak, you will see now. Devise is typically implemented recursively, following in structure similar to the code snip below. Folks, if there is people who is not familiar with the recursion and first time ever hearing about this? Okay, just to know. Okay. Okay.
Sorry, I just want to say, I know what recursion is, but I always get confused how it works.
Yeah.
It's very complicated.
To be confused, it's fine. It's absolutely fine. I'm also more comfortable with iterative approach than with recursion. It is absolutely fine. So the main idea that I just realized that I didn't put explanation for recursion. What does it mean, recursion? That's why I asked. So basically, you have function which is calling devise, and in the same function, you're calling the same function. That's we are calling heard about, not necessarily understand it. Yeah, it's fine that you don't understand. I just realized that I didn't put some basic knowledge about the recursion. Probably I will also add it here. So recursion means that the same function calling the same function inside. Is it clear what I'm saying? So we have this function devise, and it's calling underneath this itself. This is basically recursion. Also, as you know, probably, or you don't, it's also okay. When we're doing recursion in the programming language, in the code, it's actually using under OS, using a stack. That's why in real world, you can actually replace recursion with the stack, which is I will show in next questions, how we can replace it. Okay, so, and yeah, following structure similar to the code snip below. The path recursion, there is different type of defense for the tree. This is very important foundation things, which is you should know, remember. And understand how we have different ways, depends on the task. And sometimes on the type of the tree, we have different way how we want traverse. And it's very depends on the output which we want to reach. Yeah, so we have pre-order traverse, which is processing first node, the parent one, and then going to the left, all the way to the left, because this is the recursion. Once it will traverse all the nodes on the left, it will switch to the right. In order traverse, it's starting from left, traversing all the nodes on the left, then it will process nodes, and then process root, and then it will be traverse the right nodes. So this I put it here how we are usually choice for tree, but yeah, I think let's cover this one first. So when we're speaking about pre-order traverse, this is the example of tree. We're starting from root, then we go all the way down to the left, and then we are processing right node. So means it will be 1, 2, then it will be 4, and then it will be 5, and then it will be 3. The opposite, in order traverse, it's traverse for first left nodes, then it will process root, and then it will be traverse right. So means here we will reach first the left node, we will process it, then we come back to the 2, we will process it, and then we will process 5. Next, we will process 1, because we traverse everything on the left side already here. Then we will come back to the root 1, and then we will process the right 3. With post order, we first will traverse left and right, and then root. So here first again left, then 5, then we will process our root, then we will process right sub 3, and only at the end we will process root. So means we will process first left sub 3 here, and then we will process the right sub 3 here. So pre-order is the most common type of DFS. It's also used when we need to process the root. So it's not really very clear for you probably now which one to use and when to use. Because today we will cover mainly a basic one, how to find path, diameters, and height of the tree. And then we will cover BFS. So I think today it's really not clear for you which one to use and what time. Next week we will cover more advanced trees, where you will actually see when we use which traverse and why. So, for example, in order traverse, we quite frequently use for binary search tree in order to return the output in order. So, any questions for now? Okay. Now, breadth first search. Breadth first search traverses the node of the tree level by level. It processes the node at the presence level before moving to nodes at the next step left. So basically, it's processed this way. It processes one level, then it will process the second level, then it will process the third level and the fourth level. BFS is typically implemented iteratively using queue. BFS never implemented recursion wave. Only DFS is using recursion way. And BFS using queue underneath. DFS will use stack. So this is the snip code when we usually and how we process the BFS. It's used to find the shortest path to specific destination or process the tree level by level when it's important. Yeah. So we will cover two tasks today with BFS and 2 tasks with DFS. So any questions?
Can you explain, are you going to cover the logic of BFS in code in the coming questions, or are you going, or can you explain this and the DFS code? Because you know how you do dry run for the code. So I just wanted to understand, are you able to do that now, or will you be covering that afterwards in the, challenge problems?
Yeah, I can do dry run quickly here. So basically, we're putting in the Q4 here. Once we enter the while loop, we have a condition when we are stopping Q, when it will be empty. So we're popping off our root here. We process this node, whatever your function is doing here. You process 4 first. Then you're adding into your queue 2, and you're adding 5. So here you will add 2, and here you will add 5. Amar, you have a question?
Yes. When you say I have 2 questions. You said to get the way you get to the node to process it depends on the method you're using. So in breadth first search or depth first search, it's the way you get to the node to process it, and processing the node meaning to run the function, right?
Yes. Yes.
Okay. So in depth first search, how would you then process the node? Don't you have to get to it first from the, like if you go back, sorry, a little bit up. Yeah. In the post order traversal search, you said how would you process that in the graph, in the tree? You would go from the root down to you process the left subtree first before you get to the right subtree.
Yes.
Yes. So, and then in order. My question, I think, is that in order. Can you explain the in order one more time, please, on the tree, how to get to the nodes?
Yeah. 1 second, then I will finish with BFS.
Yes, please. Sorry about that. Go ahead.
No. So we have BFS. We're putting here root, and then we are putting 4. So next we're putting 2, and we're putting 5 here. 4 is already not in our queue once we pop out of the queue, right here. So why we're using queue? Because here we first in, first out, using the characteristic of the queue. Means here we will process first 2, and then we will process 5, right? So we on the next iteration, we will process 2. We will start from here. We will add to the queue 1, and we will add to the queue 3 here. But on the second iteration, our queue will look like this. It will be looks like this, right? Next, we will process 5. Why we're using queue for breadth first search? Because it will give us confidence that we are processing them in the right order, as it required for BFS level by level. Means next node will be here 5. We will remove it from queue. And next, as it doesn't have left, we are checking here if not left is present usually, if it's null, if it's not. And then we are putting here our 7. So will looks like this. Again, we have our level in our queue. We're starting from 1 here. 1 doesn't have any child. We will process it. Then we will process 3. We will popping up. There is no node left or right. We don't add anything. Then we will process 7. Once we will process 7, we know that has 6. We will our queue will looks like this at this point. 6 doesn't have anything, so we will go out of this. But all the 3 which we will process, it will be processed in this level order because we are using queue here.
So okay, that made sense. Now I have one other question before you move back to DFS. You know, you showed the representation of a tree node class earlier, right? When we start this function, yeah, so that's self and val, self.val. So how do you build the tree node? Because you're only providing the root node to the first time. So how do you build the connections between the left? So how does it? I mean, I don't know if that is done somewhere under the hood, or if that.
This is actually a good question. Yeah, this is the good question. I don't cover it here in the lecture. Somehow I didn't think, but in all the context, I included the function, which is actually building tree. But this is a very good question, how we are going to build tree. So if you want, you can look at this function.
Yeah, okay.
How I build. If you want, let me, because for graph, I will certainly cover this topic because we usually building graph, but for tree we usually receive the ready tree. That's why it's not didn't click for me. That probably will be interesting how we're actually building tree.
Okay.
What I can do, let me have it here. So how to build tree. And probably I will cover it as a next time, or I will think how to cover and include it.
Okay.
But this is a very good question. Yeah, this is a lot of makes sense, and I will include better recursion terminology.
Yeah, that's it about this one. I think you were explaining DFS after this once again. If you can do that, please.
Yeah. Yeah. So let's take this snip code. Okay. Let's try to dry run here. Let me think how to explain. So we will have in this code, so we will receive node. You usually receive node as in the linked list, just node, which will be our one. So you have the phase here. By the way, we will cover some recursion here, but it is not in order. We will cover post order. So it is when we come first, we are going down, means we are sending 2 here. Then after 2, we will send 4, because we are still calling each other, right? Here. The face and the face here. Usually, I included this code snip, but I will explain it that we always has base case. Base case meaning that once we will reach the 4th, we will check if this node is null. If it's null, then we are returning from this recursion. This is how recursion is work. I will cover in depth once we will go to the task. Once we will reach 4, we will hit the base case, where we will realize that we need to go out of the recursion function. And then we will return it. We will return the first value, will return 4. First it will be null, then it will be backtrack, and it will return 4. Then in this code, we will process this 4, which is we return from recursion function. Once we will process it, we will go to this function, which is devise write. From devise write, it will be here, because we are processing 4. Here will be our 4 again, because we know that 4, it doesn't have anything. So we will return again to the 4. How it looks like. This will be null. This will be null. One second. So we will start from the face. First, we have this one. 1. We will receive 1. We will start from left, because first the face function is calling for the left. We will go 2. We will go 4. We will hit our base case. We will backtrack to the 4. We will process 4. We will go to the right node of the 4. We will hit again base case. We will back. Once we will back, we will backtrack to the second this level of 2. As we processed everything here, we will process next our 2. So we process this backtrack. We are backtracking to the 2. Next, we will means here will be our. This is 1 second. Wait. This our devise, which is right. And next, we will backtrack to the this devise level. Next means once we will go, so we will process 2. And next, from the 2, we will hit this line. Devise not right. So here we will process our 2. We will start, so we will call devise 2. As we we currently on this line. It will be 2. We process 2. Next, we're going from 2. We're taking the right node, which is will be 2. Right node, which is actually 5. We will go to the 5, and we will go to the null. We will 1 second. I'm thinking. So we took 2 here. We will process right. We will go to the right. We will backtrack to the null. We will return it. Right. 1 second. I'm thinking. So we will have right. Yeah, we will go to the right devise. Then we go next. Once we will go with right 5, we will hit again this line, which is will be our 5 left. We will hit null. We will come back to the null. We will process our 5. 5 will process the right one. Right, there is again null. So we will backtrack to the 2. but 2 we already processed. From the 2, we will backtrack to the 1. And as we process these 3, we will go again. This will be process node 1. From the node 1, we know that we have already been here. We will process 3. 3 will be started processing again. Left, it will hit the null. It will come back to the 3. 3 will be processed. Then we will try to find if this 3 has actually right. It will backtrack null. Everything is processed here, and we will come back to the level of 1. Is it clear? If it's not clear yet how the recursion is work, we will go in deep in our next a couple of questions. If you have some questions now, ask.
So just to reiterate, to see if I quickly know how this is done. So you start with the root node, and
Yes.
then every node you ask it to the depth first search. So it goes and looks for child nodes.
Yeah, it
And
will
then
go.
and it will go as deep as it can until it hits the base case.
Yes.
If it hits the base case, then it will backtrack and process the node above it.
Yes. So basically what you should understand, once you call devise not left, it will go all the way down until it will hit the base case. Base case, usually we check null. So once we will process it, we will backtrack. Once we will hit this, means we finish with this line, we hit backtracking, we'll switch to this line of code. We will process this node. Then we're trying to enter again recursion, but with different value. In this case, we're calling right? So we will go all the way. So we call right. We
Hold on 1 second. Now I have a question about the 5. So you've checked 4, and it's got right node base case, left node base case. So you go ahead and process the 4.
Yes.
But how do you get to the 5 without getting to the 2 first, then to the 5?
No, you're going to first. You're going after 4.
Okay.
You're going to first.
Okay, and then you go back down to 5. Then check if it's okay.
You're
Got it now.
processing 2 here. You're processing 2 here, and from 2 you receive the right node.
Okay. Gotcha. Thank you.
But the main things that once you enter to devise with 5 here, you actually will go again through these lines of code. Means from the 5, first you will check if there is left node. If there is not, like in this case, you hit base case, you will come back to the null. You will process your 5, and only after this you will process your right, because it's different. Once you starting from root and you're processing first all the left nodes, but once you backtrack, you start processing the right node. So you're going again through all these lines. You are not going to the same way like we're doing for right. This is probably important also to understand. Because you're calling devise and you're entering and you need to process all these 2 lines above. Let's see how the task will go. If we would need to stop more to make more comfortable with recursion, so we will stop and we'll try to cover more on the dry run. Are you good, folks? But it's good if you ask me questions, because I can explain the way and I can miss something. But when you ask questions, so it's I think it's helpful for everyone and for you to ask and to understand. Because I miss a lot of foundation stuff while I was preparing this lecture. Okay, recursion. The template is starting point for solving binary tree problems with step first, which takes the base implementation of the phase from the previous section and adds return value to each. Also, just heads up before we will go, there is not different type of recursion. First, we will cover the most simple recursion, which is just return value, as we discussed just traversing. This is we calling return value. Sometimes recursion depends on the complexity of task, will require it to introduce other global variable, or will introduce some variable inside of method, which is will require us to introduce helper method. This is just heads up, we will cover it. So recursion. The template is starting point of solving binary problem with depth first search, which takes the base implementation of DFS from the previous section and add return value to each recursion value. This is the code snip of DFS. In DFS and recursion, we usually are using this interchangeable. This is the recursion method. In each recursion method, you will always have a base case. Otherwise, you will end it up that you are not able to exit the recursion function. So it's very important to have a base case. Here we will, so it's base case, then we have our function, recursion function, which is we're calling. Here we're calling, and then we return value over here. So this is the snip of the recursion function, how it should looks like.
Sorry, what are we returning in that? So when you say return value based on left and right, if there was a left node and also a right node, would it do, for example, for 2 in this tree, what would this function return?
This the template. Template. So basically, depends on what you need to return. By the way, this probably also. Let me see. I will tweak this one later. Depends on what in the task will be asked. This probably will be a good example. I will make it better too. So you're calling here left and right, and depends on what task has been asked, you return the value. You will see now into example, because we will take the we will dry run it. Let me just probably make clear. So what we did just now, we cover the tree topic with the main terminologies. We cover how we are going to traverse tree. This is the just a code, a recursion code, which is required introducing the function, introducing the base case, and introducing the return value. Depends on what needs to be done. This is just how we traverse, how we can traverse, how we can process nodes. Now that we're taking task, so for example, problem sum of node, we can decide how we are going to process all the nodes. In this case, we're processing left, then we're processing right, and then we are processing the root. In this case, we're using post-order traverse. So what I just explained, it's just how we are going to traverse a task, depends on what has been asked for us. Return value, it means the calculation which just needs to be done when you process trees and what is asked in the task. So how to make this clear? What I just covered, just example how we are example how traversing trees. Now we're trying to apply this knowledge to the actual tree questions. As I mentioned, most of the tree question required, not required, but you can use recursion as a iterative solution. For recursion problem, now what I'm trying to explain, you will have function, actually. This is just example. how we traverse. This is not a function. This is the actual function. This is the actual recursion function, which is all the time recursion function should include base case, should include code how you traverse your tree, and then return the value. Depends on, I will explain what is this return value is mean. Yeah. Is it clear for now?
Yeah, just to
Yeah.
this is, I think, a very important point. So at
Yeah,
any point when you're using recursion, you always keep track of your root node and the right child and the left child, base case. All these things you're keeping track of those, and depending on what happens when you hit base case, what you do. When you hit each node, you either traverse deeper, or like at some point you run your return value. Like the things that you keep track, is it always the same regardless of what you're using, depth first or breadth first? Are there things that you always need to keep track of, like the root node, its children, base case, and return value? Is it always the case?
It is always the case for devise and for recursion function. Always the case to have base case, because if you don't have base case, you won't never go out of your recursion function. You will keep going to the recursion. You will keep going
Infinite
to
loop.
infinite loop. Yes. So for the recursion, because you should keep always in mind that you have to have base case. When a recursion function comes to the solving tree, you should know three types of the traverse of tree, which is related to devise exclusively. We have to devise exclusively because depends on what needs to be solved in the task. You should to choose the right things. How you will choose? Because you should understand how you process, in which order you process the nodes. So you should know, in this case, you process root, left, and right. In this case, you process first left subtree, then root, and then right subtree. In this case, you process first left, right, and root. Once you know how you can traverse trees, in which order, you can apply to the solving of the tree. So it is here, this part of code responsible for how you traverse the tree. And it will be very dependent on the tree question. This is something which is related to the recursion. We will see how iterative solution work. In this case, when you will have iterative solution, there is no base case, no recursion function inside. So this is plain, this is focusing only on recursion. But if you will take a look here, this is the iterative solution. It is not base case, we just checking if root is not, we just right away returning 0. So basically you can live without this one. In iterative solution, you will use stack. Quite similar code, but because you're using stack, and it is having different characteristic compared to the queue. That's why, but the code is similar. Just because of stack is last in. What is this? LeetCode last in, first out, and for queue it's first in, first out. So it is just difference how you process, in which order you process your nodes. So I hope I answer your question. Did I, Amar?
Yes, thank you so much. Clear.
Okay, cool. So how we traverse now? How we use a recursion function to solve tree problem. So let's take a first at this one. So we have a binary tree, and we need just to sum up or all the nodes and return the total sum of all nodes. So from the description, is it clear what asked? Okay. I add some why recursion works well. It will, so tree is inherently recursive structure, as I tried to explain. Each node itself, the root of the subtree. Each nodes contribute to the total sum, can be defined as node, tree is inherently recursive structure. Why it is recursive? Because it is has subtrees. This is our left subtree, this is our right subtree, and each subtree also divided on the smallest one. Recursion itself, it is about to divide the problem into smallest sub-problem. To solve this sub-problem on the level of little function, to backtrack, to make a computation, and to backtrack, and to make computation and return the actual answer. This is the idea of the recursion, that we can divide recursion on the smallest one to solve them and backtrack. This is kind of characteristic why we use a lot recursion in the dynamic programming, because dynamic programming also about just to split the task on the smallest one and to solve it. This is kind of family of the problem, which is family of the problem where you need take the task and you need to split on the very small sub problems in order to land it with the answer for the task. That's why I'm emphasizing a lot on the recursion, because it will give you foundation for the graph and for dynamic programming as well. So, as I put it here, each node contributes to the total sum, can be defined as, we will have node value, we will, so if you look at this one, we have our 4. In order to have the total sum of these 3, we can count this like 4 plus 6 and plus 2, which is give us the total, the sum of all nodes in the binary tree. The same things going like we will divide it into sub-problem. Here will be 1 and here will be 3. Eventually, it will return us 1 and 3 here. And here we will say, okay, 2 plus 1 and plus 3, it will be our 6. Next, we can calculate the same way. We will take 7. For the 7, we will backtrack 6, 9, and we will calculate 22. And in order to calculate the total one, we will backtrack 6 and we will backtrack 22. And here we will have 4 plus 6 plus 22, and eventually we will return the value of the 3, of total sum of the 3. So in this case, if the current node is none or null, return 0. I mean, none, it is a null actually. So we will return 0. Means here, 1 doesn't have right and left. It will be our base case here. We will return back 0 and we will return back 0. Recursive case, return current node's value plus sum from left and right children. So this is the code. I just realized that I put it quite in advance. So actually it could be looks like this. And here will be our right. And here we will return our left. And here we will return our right. So base case, then we are calling the same function. We're calling this sum of nodes. Recursively, we will call sum of nodes until we hit our base case. Once we will hit our base case, we will go to this row. We will again enter to our case, and we will first call this function. And once we will hit here, we will backtrack here, and eventually we will return the value. So this is try run, which is I put it. Let's just do walk through.
Lydia, is this, so here we're doing left and right? So is this in order traversal?
This is no, because we are going left, right, and then we are processing it. This is our post-order traverse.
Okay.
We left, right, then we are returning to the root.
Right.
And in this case, we process first left, then we process right, and then we are making the total sum, because first we need to count what is the sum value in this subtree in the left. Then we need to find the value on the right subtree, and then we can return the total sum. But this particular task can be solved with a different way. So because the idea is just to make the sum. So there is no particular requirements how you're going to traverse, because the FS is itself is including traversing all the nodes the same way BFS you can apply here. So there is not the strict or strict requirements which how you're going to traverse, but particular in this just code it is post-order traversing. But all the tasks which I put it here, I believe we will come back, but I believe it doesn't require particular things. I was planning to cover when we required particular traversing in the next session. Someone has a question? Oh, okay.
Yes, really quickly. When you have an interview question,
Mm-hmm.
how do you know which method to use, or is it like by experience, or do you sometimes use a way and then hit a wall and go, this is not going to work, I'm going to use a different method? Or how do you so like
yeah for today we're just learning how comfortable to be with recursion and just knowledge of traversing. Next class I will explicitly tell when and what needs to be done. The one thing which is we will cover here, you will write most node. So there is particular set of tasks which is you right away know that it is breadth first search. But in particular lecture, I just don't want to confuse you with how to choose it. It's more advanced topic.
Thank you.
There is, I can answer. There is some questions which is will require to know you how to process in which order. Yes, there is. You will see next session. But today, so for example, we will solve 4 problems, and probably the only last one will require to solve it just with breadth first search. But it is can be solved with any traversing. Okay, so dry run. We entering first. We call our this is some node. We call this function. So this is the first entrance to our recursion function with 4. Then we're checking if root is none. Here it is not none. It is 4. We are going to call 2. We are going to call some nodes. This is still stack. So we are going here. Don't be confused, folks. This is some nodes 2. This is not where we are going. This on this diagram, we are going to sum of nodes. Then we are going to, this is sum of nodes. Then we are going to sum of nodes 1. Here we will hit our 4, then 2, then 1. Here we will hit our base case, which is none. It will return our 0 and 0, and it will sum up our not root value, which is root at this moment will be 1. I think maybe like this will be clear. This is 4 here. Next, it will be our 2. We're entering here with 2. We check if it's not null, it's not null. Then what we're doing? Then we are saying here, it will be our 1. We're entering this function with our 1. Next, we check if it's null, it is not. Here we will hit our null because 1 is having explicitly null, pointed to the null as a left child. Here we will enter our function with null. Here we will check and we will return 0. Means in this case, we will return here 0. Next, as we hit, we enter, we exit of this recursion function. It is 0. We will return value 0. Here we are going as we because our root at this moment, it's also important to understand that root here is 1. Here root is 2, and here root is 4. Now that we are exiting this recursion function, we return 0 here, but our root is still 1, so we know there is again null. We will enter to this recursion function again with null. We will check, it will return us 0 here. It is our root 1. And next, once we process these recursion functions, this and this, we will go and count here. Root value will be 1, here will be 0, and here will be our 0. This is the line of code here. We return this value. We return to the level of 2. We backtrack. So we basically process everything on the left side. Once we process, we return 1. And we return this 1 is here. It will be our 1. This is particular, this line of code is doing this. Is it clear? And when we're speaking about null, which is returning as 0 here, it is this line of code which is returning as 0 here, because we hit null and we're returning 0. But once we process everything, as we have value, we will return 1 on the level back to the 2 here. I hope it's clear. So maybe, yeah, we're calling sum, then 2, then sum node. We backtrack back to this node. From the 2, we are going to the branch, which will be our node 3 here. We will do the same, starting from left and 3. We will backtrack 0 here. We will backtrack 0 here. We will count, it will be 3. At this point, our here will be return 1, is this line, and here will be return 3. And then we will calculate this return. We will return on the level of 2 here. This is the answer. Next, from the 2, as we process everything here, we will return it to the 4. So we will we will return 6 here. We will return to the 4, 6. And we start processing the right subtree the same way that we did for the left. And at the end, it is exactly this row of code, which is eventually will return as the total sum of the nodes. If it's not clear, folks, ask. Don't hesitate. Ask as many questions as you need. Yeah, go ahead, Amar.
Sorry, I don't mean to confuse anyone,
No.
but when this tree is called binary tree, right?
Mm-hmm.
So that means each node will have 2 children.
No, not necessarily. It could be one child. As I mentioned in the terminology, there is up to 2. It means it can't be more than 2. But
What about balanced tree? If it's like a balanced tree, would it have 2 children?
No, it is not balanced tree. It's just
Okay.
binary tree.
Binary tree.
When we're speaking about the binary tree, as I explained it before, it could be this one. Oops. So this is also binary tree.
Oh, okay. I thought binary means each node has 2 children.
No, up to 2 children. So binary tree is the most primitive tree out of the other three. It's not self-balance. It's not a binary search tree where we're speaking about on the left side, we are keeping values as mean then root, and on the right side we're keeping value is more than. So just folks try to abstract from knowledge which is you have around the tree and focus just on binary tree. Binary tree is the most primitive one at this moment. So we're covering the most foundation things for the tree today.
Thank you.
Nope. This is the recursion one. For me, iterative solution is always more easy to implement, but there is advantages of having the recursion because it's very small. This is the code which is required to solve this task. And this is the code iterative solution which is required to solve the same task. For depth first search, we're using stack. Let's just traverse and see how it will go. So we're putting a stack for here. We're putting our first. We're including total variable where we count it. So next we're doing, while stack is not empty, we are going to traverse. We're popping up here for. We are counting our total. Our total will be 4. Here we're checking if it doesn't. In this case, you can push left or right. There is no particular order. What next? Here you're checking if it's null. If it's not null, then you're adding to the stack 2. Here you are adding to the stack, so it is our 7 actually, and there is our 2. Next, you're going to pop up our 2 plus 7 and plus 2 in next iteration, in next 2 iterations, and you're adding to the stack. So basically, this is the dry run. You pop 4 add value 7 and 2. You pop 2 add value stack 7. 3 and 1. You pop 1 because it is a stack, right, folks? So your add value 7, 3 is still there. Pop 3 add value stack 7. 1 second. You pop 1 here. Okay, because it's null. So there is no left and right. You didn't put anything. Then you pop 3. There is no left, right. So 7 is still there. And then you're processing 7, 6, and you count the total. Is this code understandable? Okay, this the another way. There's this one iterative solution. So for a long time, I didn't feel very comfortable myself with recursion. Very long time. I can't still that I feel comfortable, especially during the interview. For me, easier to come up with iterative solution rather than with recursion one. What helps for me with recursion to make the same dry run, like I explained it to you here, folks. And there is also some visualization tools where you can enter your tree and just to see. But for me, best working when I doing myself this on paper. Like I'm going down. I know I hit base case where I hit this one. So basically, you can draw on the paper just to become more comfortable with the recursion. But again, it's not a very big deal if you are not very comfortable during the tree interview. I would say probably for backtracking in dynamic programming, it's more required to be comfortable with recursion, but it's a very advanced topic. And I know a lot of companies is restricting to ask any backtracking in dynamic questions during the interview. So if you're not very comfortable, every time you can fall back to the iterative solution. And there is no pros and cons. Is it clear on this task? Okay, let's try to solve something similar. Maximum depth of binary search. Given the root of binary tree, return its maximum depth. That is, we have definition in this task. What is the depth? The number of nodes along the longest path from the root node down to the forest leaf node. Sometimes it could be missing. Then you should explicitly ask what under depth, path, or height they mean, because it could be very specific to the interview. So we need to find the maximum depth of the binary tree. The maximum depth will be this one, 1, 2, and 4. And maximum depth will be 3. As in this case, the number of nodes we're counting. Sometimes they ask the depth, but they mean they are only ages. In this case, it will be 2, because we have 2 ages here, not but 3 nodes. Is it clear from the description what needs to be solved? Okay. Yeah.
Hi, Lily. I might have missed you. You mentioned that sometimes in the description they don't give you what information, and you should. Sorry, I missed it.
Yeah. What under depth they mean. So, for example, just imagine that this one was missing here.
Okay,
yeah, this description, which they explicitly give you. I did give you some terminologies here. And in these terminologies, we actually, in the depth, we are number of ages. But in this case, in this task particular, they mean the depth is the number of nodes. What is the difference? It is, if it's ages, then we will give the depth if 2. But if it's nodes, we should count the number of nodes here. It will be 3 instead of counting ages. So this is kind of things which is nice to track during the interview. Okay, given the root of binary tree, return its maximum depth. Why recursion fit here? Each subtree itself is a tree, as we discussed on the previous task. Again, we will dealing with our subtrees. In order to find the maximum depth, we need to find maximum depth of the left subtree or of the right subtree. And then we just sum up the root nodes. That's why, again, recursion kind of fit us, because first we need to find depth for this subtree, then we kind of find depth for this subtree, and then eventually we will find for the whole tree. Is it clear what I mean under subtree? Because the longer tree we have, the more subtrees we have. Okay. There is something been here, but it's missing. I don't know where what I wrote here, folks. So recursion code. Will be like this. Step. And it will be again right. Left, which will be and instead here we will put this one left and right step. So this is very similar to what we did just above, right? We have again our base case. We are processing first left subtree, then we're processing right subtree. We find the left step on each level here and here. And then we will return our kind of answer here. So it's just different how we are processing nodes. Processing, it's again what needs to be solved on the sub problem of the subtree. So if we go with dry run again, we are entering our max step with 1. Then we go to the branch, which is max step 2. It is here, this code. Next, we are going to the for. So our base case, in this case, return 0. We backtracking here. We count it 1 because our root is has. It's not value. We just count first node, which is not null. And between here and here, it is both 0. So basically, we're ending up that depth on the for this child 4 leaf node will be actually 1. We backtrack this answer to our parent, which is 2. Here, so means we're sending 1. As there is no root right node, we return 0 as it is here. 1 and 0, and we will have here 2. So on this level, subtree, the depth of this subtree will be 2. We will backtrack this knowledge to our parent. Now we need to process the right subtree. So there is no left and right child. There will be depth, which is 1. We will backtrack to our root. And on this level, we will choose between this max depth and this max depth, which is 2 and 1, and we will return our answer 3, because this is our maximum depth of this subtree. Iterative solution will be, could be solved with DFS and BFS. I believe I posted only BFS solution here, because DFS was quite complex. So you can solve this with iterative solution using queue. Before I will go, because there is a kind of important focus on this. Is it clear regarding the recursion? Should be more comfortable now, because it's very similar to the one which we just solved before. Okay. And there is a lot of questions on the tree, which is including actually this kind of quite straightforward code solving with recursion, like you're having base case, your traverses the way you want, and then you return and then you process. Or you can process and then like traverse, depends. So, but a lot of tree problems can be solved with this template of recursion function. So once you will be comfortable, you will quickly to solve it with recursion. Let's go and check iterative solution. We can use BFS level traverse using queue. Each level you process, you're adding +1. 1 second. Just will check this code. So queue offer left. Number of nodes at the current depth will be and return depth. Okay, yeah. So in this case, we are not looking into subtree in order to find the maximum depth either on the left or on the right. In this approach, we're doing a level traverse, and on each level, we are accounting new depth. Means on this will be 1, 2, and 3. Actually, first we will start from 1, 2, and then we will hit this level, which is including only left subtree. But it is a level which is including, which is give us the maximum depth of this tree in general. So no maximum value between the left and tree and the right. We're just going level by level and counted how what is the depth actually by tree. With this kind of things, which is very very related to BFS, you will quite frequently use this one, and this will be quite frequently used in the graph as well. This is the tweak, how we are accounting the level of the tree. So we have queue here. We're adding our root, which is just will copy. So we're adding here our one. Again, we are going while. Now we can detect our level size on here. It will be a size of the queue, and it is 1. On this, what does it mean, level size? How we are know that this is our level at this moment. We have just 1, and we know on this level we have just one. We just have one node, and we go. That's how we're fixing how many nodes on the same level. Next, we introduce our for loop here, and it will be 1. We know once we traverse once, means level is out. What will happen here? We pop up just here, our 1. We will keep adding here our 2 in our queue, and here we will add our 3. So level will finish because size is 1 here. After level is finished, we will increase our depth variable. This is first level. Next, our queue, we are going out here, and our queue size at this moment, because it's including 2 and 3, the level of this tree, the size of this level will be 2. We fix this level. We know we need to traverse all these childs in this level, and then we will just increase it. Is it clear what I'm trying to understand? Because this is very also important concept, how we are differentiate levels in the tree with breadth first search. Once level here is detected, it will be 2. We will process first all these 2 and 3 in this 4. Means on the next iteration, there will be just 4 in the queue, but our depth will be here too. Level here will be 1 again. It will be 1, and we will process here 4 node. everything will be null here. We will come to the queue. Queue will be empty now, and we will go out. But our depth will be free. So we will return answer 3. This is how we will count the depth with breadth first search. Any questions? Overwhelming, I believe, how we're jungling between DFS and BFS. I can think, I can feel it. The main of this foundation tree today lecture to make you be comfortable with recursion. I add iterative solution to all this task just to keep it and that you understand that anytime you can actually solve this with an iterative solution. But the main idea is to make you very comfortable with the recursion itself.
Livia, can I ask you a question about recursion, please? It's not maybe related to trees, but if you can just show me a recursive function. Okay, so the sum of nodes, let's just take this example. When as you traverse the tree, you're recursively traversing the tree, correct? So let's say you reached the node 2, which is your left node. My question is, for each node, does it go and look for left and right node and then keep doing that until it reaches a null node?
Yes. See, if you look at this recursion function, this is the starting point. We are first entering here. As base case, let's skip base case just to skip, but it is very important to have this base case in the recursion function. Then what we're calling recursion here, that you're calling itself inside of yourself the same function. But you are sending different parameters here, right? You can send root here, but it will infinite loop because you will keep sending the same root. You will just again will enter. So this entering point, then you're calling yourself means you will come from this line again here, but with different parameters. It could be the same parameters, but in our case, it's different parameters. You're calling yourself with the different parameters. Then again, you calling yourself with again you're calling and calling and calling while you hit this base case. Then you can actually from this, see, we are assigning to this left variable something here, means you hit this base case and you return here something left. Once you exit from this recursion function, you assign it something here, you process next line of code. What is with recursion may be also important to understand that you're calling yourself, you're stuck here. You're stuck on this line until you are not finished this by hitting the base case. Means this code is unreachable for some period of time until you are calling yourself here. Once you, how you exit this at this moment, you exit this with here. Once you exit here, you move to this line, but it is again recursion, okay? You enter, you're calling this function here. Your entry point here. you hit this line code, but you also hit this line of code as well. Means you're calling again yourself as a recursion. And if so, even though at some point you process it already here, but you are calling yourself again here, but you're going through these first lines of code, means you again calling here, and again you're processing. And at some point, when you exhausted all the solutions, you will process this one and this one, you will return this value, and eventually you will come here. And you will return value, which will return value either here, either there. That's how it is going up. So you reach 3. That's why when we are going with recursion, it's usually very well represented to this one. You're processing, you hit base case, you backtrack. You process, you backtrack to this level, you start processing code here. You again hit the base case, you backtrack, then backtrack, and backtrack.
So I have 2 questions. One is every time the sum of nodes is called, the root is changing, isn't it? And when we actually come to that line where it says return, root.val is the last root.val.
Yeah. So for this, when we are hitting null and null, root will be 1. Once you backtrack here, it is your root here. 2 will be root here. But there will be value from left and right, this one and this one, because you process. So in this case, you also have left and right when you're hitting null, because it's 0 and 0. You're anyway returning the value here. Yeah, the one thing which is when you're working on this level, 1 and 3, your root is 2. When you're working on this level, your root is 1 and or 3, whatever. And then when you're backtracking to 2, you're working with 2, but your root value is here 4.
But where do we in these 4 lines? Where do we reassign the root? I don't see that we reassign the root.
We are not reassigning. See what happened. Once enter, it will be 4, right?
Yeah.
This is the root.
Yeah.
You enter. You're sending here root left. It will be your 2, right? And then you're calling this. Means your root now is 2 here, because you're calling itself with the variable inside, which is you're calling root. And that's here. You're not really reassigning, but you're calling your recursion function, which is taking root as a value.
Yeah.
And you're entering here with 2, and from 2 already, from 2 here, you will say that it is 1. Once it will be 1 here, you will enter this function with the 1, which is your root will be, and from root left and root right, you will call actually. This is very good question. Thank you, Moina, for this question.
No worries. Sorry, I'm asking a lot of questions. One other question is, looking at the code now, the way we iterated, I feel that every time for all the left side nodes, right? Like for, let's say 2, 1, and let's say 1 had more children, then for the left node, I would never process the right node, is it right? But for a right node, I will always process a left node and a right node. Because you see, if you see the order of how we are processing the nodes, left is processed before right. That means before left never knows its right node. I mean, its right child. But for a right node, it knows its left child and a right child.
No, you're processing and left and right. See, once you reach 1 here as a root, you will process both the children, left and right here. You will go here, you will hit your null, you will come back to 0. From 1, you will again hit this line, which is again will hit null, and you will come back with 0 here. For each node, you are processing left and right. Then you will backtrack, because you now are processing this line of code left. You process it, you just process it first, but you processed left and right here. Just for this root 2, your left child is 1, your like left sub-3. So you basically process it. You process it and you come back, and then you hit the right. So what I'm trying to say, for each node, you first process left, then you process right, then you're coming back. Same here. You're taking 2, you process first 1, your left sub-3, and then you process 3. And then you're only processing the root. The same for 4. You're just starting, treat it, that's why I ask. This interesting things which you should understand. This will be left sub-3, and on this right, it will be right sub-3. For each node, for 2, you will have this one on this side. It will be your left sub-3, and on this side, it will be right sub-3. Meaning, for each node, you are processing the sub-3s. First left, then right. For 2, you're going to process left and right sub-3. All the time you will process.
Okay. Okay. Thank you.
No? Okay. Next task will include also recursion, but it will be a little bit complicated recursion. And this particular task, I looked at iterative solution, but iterative solution is very complicated to solve this task. That's why I didn't even include iterative solution for this. Let's try to understand how to solve this particular task with recursion. I will explain what is the difference compared to one which is we solved. Okay, diameter of binary tree. Given the root of binary tree, write a recursion function to find the diameter of the tree. The diameter of binary tree is the length of the longest path of edges. This particular saying again, that path, it is edges, and it's not nodes, between any 2 nodes in the tree. This path may or may not pass through the root. So in this particular example, the longest path and our diameters will be this way. Or it could be this way. And diameter will include 3 edges, 1 and 2. So this is the diameter of the binary tree. From the description, is it clear what has been done, what has been asked? Okay. Let me see. Just the diameter of binary tree is equal to longest. So now let's break down to calculate longest path that passes. If I'm at node in the tree, what value do I need from the left and 3 children to calculate the diameter? The max step of the left, and yeah, this tells us, okay, base case and global variable. So this is, description. How we are going to find the diameter of the tree. It is, in this particular example, it is passed through the root. But there is, sometimes you have tree where it not actually pass the root. But the idea is behind to find the longest path, or the actual diameter of the tree, which is the longest path, is to find depth of the length and depth on the right side. And then calculate the actual longest path. Depth we try to find here. And yeah, so we were looking into how to find the depth of the tree in this task, right? This problem sum. Yeah, maximum depth of the sum tree. So means if we will break down how to calculate the longest path that passes through the node in the tree, as shown in diagram below, the longest path that passes through a node is equal to the maximum depth of the node of left subtree and the maximum depth of the nodes of the right subtree. where the depth of this tree is the number of nodes on the longest path from the root of that subtree leaf nodes. At each node, we want to find the maximum depth to use to calculate the length of the longest path that passes through the node. With that in mind, we can solve this problem using this formula. So first, we want to find the depth on the right and left subtree, and then maximum, I believe maybe this example. If we will add 7 here, so then this one will be our longest, actually. For this, in order to find, means we will find how we will ending up with finding the longest path. We will process left and right subtree, and we will process it for each node. We will process it's on the latest level for the root. We will compare this one, and we'll give and we'll compare this one. We're not comparing this one left and right. We will just make the calculation eventually. In this case, because the root is actually passing here. But it could be that actually, let me see if I will put this example, I believe.
We have one quick question. When we say diameter of the tree, it's not supposed to pass the same node twice. Is that right?
Yeah. 1 second. Say again.
So, like you were just showing, if we had that node 7, isn't it? The longest path is from 7 to 3, correct?
7 to 3. Here, yes.
But what,
this example.
but it also looks like 7 to 4 to 2 to 1 and back to 2 and back to 5. That is also longest path, but that means that one path is covered twice. Is that incorrect?
It is correct. That's what I'm trying to draw. Now we have this one path, the longest one here. It is 4 here. It is also 4. But for example, if I will put let me. Yeah, so in this example, we have 2 longest diameters. So we won't care which one to return. It could be this one, which is also 4, or it could be this one, which is also 4.
What about covering 1? So let's say 7 to 4 to 2 to 1, back to 2 and 5 and 9. What is wrong with that part? Because you can come to 9 by going back to 1, isn't it?
No. This is this won't be your path. Your path should be like this or like this, because you're coming back.
Yeah.
No, it can't be. It should be like this.
So it should not repeat.
Age, because you count twice time on this age. That's why it looks for you it's as it's a long one. Okay, yeah. So just to let you know that we are counting this diameter as well, and sometimes the risk could be like this. Means this diameter will be also longer one if we will go this way. But in any case, how we are finding out the diameter of the tree? So we are counting this depth, and we're counting this depth, and then we are 1, 2, 5. It's again so it could be like this, and it could be like this. if we will remove this one, so then it will be this one only, right? 1, 2, 3, 4, and like this it will be our 5. And with this 1, 2, 3, 4, 5. Yes. We can do like this, or we can put it here. It will be 11, and then I believe this will be sub 3 eventually longer. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yes. So now we have this one. In order to find the longest depth, so what we will do? We will count for each tree. Again, as I mentioned, in order to find the diameter, we need to know the depth of each subtree. On the left and right side, then we are doing the diameter. We are summing up left plus right. And that's how we decided which sub where is the longest where is our diameter. So for example, for this one, we will count 3 and 3, and it will be diameter of 6 because we have edges here. We're counting edges and not nodes. And for 1, we know here we will return the max depth of this tree. It's actually either this one or this one. Yeah, and we will summing it up. So to max depth, it will be path. Yes. So is it clear how we are counting the diameter? I believe it's exactly the question of this when Moina, you ask whether it could be the same. It can't be the same because in order to calculate the diameter, we need to find the deepest depth. And deepest depth, it could be this one or it could be this one only. And when we're, yeah, so this depth. Mm-hmm.
So are you saying what I was saying was still correct in terms of the diameter? We could cover the path between 2 and 1 or not?
No. I'm saying not. No. It should be depth. And for depth, we are not counting. It's like this. We are counting as if from our previous example. It is either this one or either this one.
Mm-hmm. Okay. I mean, I know you're going to explain the logic, but I just don't see how you can get that without repetitive edges.
Because we will count only depth.
Right.
We are not counting back and forth here. We will counting depth. How we will counting the depth of the subtree. So for this subtree, it will be our 3 here. And for this subtree, it will be depth. We will find the depth, and it will be our 3 here. And next, we will, in order to find max depth, we will use the same formula like we use here, which is max left depth and right depth.
Yeah.
And here we will take either 3 or this 3. If it will be 2, we will take 3. So we will take either this value or this value. This will give our the depth of this subtree. And then we will backtrack this 3 value to our root. The same things will be backtracked from the right side, and it will be our 4 here. So
how is it 4?
Not 4. It will be 1. Sorry, it will be 1. And here we will sum up diameter on each level. Means here will be our diameter, which is 3 plus 1. Because it is edges, it will be 4. And on this level, diameter will be 3 plus 3. And as we will introduce global variable, I will explain it now. we will on each iteration we will looking for the max tree. So basically here we first will find diameter 6, and then it will be on this level it will be diameter 4, but we will still think that our max diameter is 6. That's how we will find. So now I'm just trying to explain you how we are going to calculate this diameter. In order to calculate this diameter, we need to calculate the max depth. Because the diameter is it is the sum of the left depth of the left subtree and of the right subtree. And the main point to understand that diameter is not obligatorily going through the root. In this example, we have this one diameter of our tree. It is actually lying on this subtree. From what I just explained, is it clear? Because I will go and now explain how we are going to solve it with recursion. Okay, cool. So with recursion, it will be a little bit complicated because in this task, we need to track our max diameter on each for each subtree. As I explained it, because it's not that we will come back to the root and we will find eventually our answer. So our answer could be on each level. For this purpose, in order to track max diameter tree, to addition to our recursion function, we will introduce a global variable to keep it updated on the each level by this function, which is will take maximum current diameter, which is we found so far, and we'll try to compare to one which is we will find on each level of our recursion function. We will start from 1 as we did it before. We will backtrack to 7. We will count here and here. We will try to find our diameter and here. So from this perspective, how we traverse the tree, nothing has been changed. You see, we still have the same function, which is calling. We have the same base case. As in previous task, we also, as we decided that in order to find the diameter, here we're finding diameter, we need actually to return the value of max tree. So basically what we are doing here, we're extending our previous recursion function, which is without this, if you will close it, everything what is this function is doing is just calculating the depth of the left subtree or right subtree. But because we need to find the actual max diameter on our subtree whenever we will find it, because it's not on the root. It could be on the left side, it could be on the right side, it could be passing through the root. That's why we're including this global variable, max diameter, and we're just updating our result all the time when we need it. But again, in this case, there is one more complexity, which is we added. We're calling this actual helper function. Because if you will take a look, so for example, at this problem, when we're taking sub node, we're having just one function, and this function, we're calling this function all the time inside of this function. But to solve diameter of binary search tree, what we, okay, this is probably, if I will find my solution here. In order to solve this task, so what we are doing here, I solve it slightly different. Max diameter, so what is this? So should be a max diameter here. Will be our max diameter, which is how we initialize here. Should be initialized, okay, as a 0. will be our 0, and here we will introduce our helper function. And here we will just update our max diameter. So if you compare this one, trying to explain, this is a little bit slightly complex recursion function. In this case, we are calling this recursion return by value. Means we just calling itself this recursion inside of each other. That's it. We don't have introduce any parameters which is we are sending as a part of this recursion function. We didn't introduce any global static variable where we are updating it, and all the things which is this recursion function is doing is returning the value. Once it's hit as a base case, or it will process the nodes and make calculation and return the value. The difference now that because we are doing different calculation here, we are not returning max diameter, right? Over there, we are returning the depth, the value of depth of the left subtree and right subtree. That's why we need to introduce a helper function, which is doing slightly different calculation. But we're leveraging this function because it's returning the value of depth left and subtree, and we are updating our global variable with the value which is we are looking for. So my main point that now we are extending our recursion function. It's become our helper function. We are not calling it from the main function. From main function, we are invoking helper function, but next helper function will call themselves inside. And in order to solve in this case, we introduce max diameter, which is global function. And here, 1 second, I will remove it. And here we're just updating it. We're just updating our global function with the answer. And after we updated, we finish this helper function. Helper function will be finished here. We will go to this line code, and we will return the value of our global function. This is another template how we are solving tree problem with the recursion, but with more complex approach. It will require you introduce a static global variable, and with static global variable, it will require you to introduce a helper function, because helper function is doing slightly different. This one thing. Another thing you could solve it slightly different. In this approach, I again introduce the helper function, because during interview, sometimes interviewer can tell you that I don't want to see the global function, because global function is coming with some complexity when we're updating it. And sometimes I was as a part of one interview when interviewer told me, could you solve it without global function? If we're not having global function, again, we can't use just one function here, because we introduced the helper function, and difference between the helper function in this case, that it is, we extended it to have additional parameter for the tracking. That's why we can't use as well the same template as we used before. Just even if you, for example, your function is doing actually the same things, could do the same things, which is the main function. But because you need to introduce the different parameters here, so you need to introduce a helper function during the recursion. My main point, what I'm trying to explain you folks currently, that 2 tasks before, I showed you a plain recursion where we just return the value. But there is some task which is required slightly complex solution, which is required you to extend this recursion function to the helper function, and introduce also a global static variable, or to have this helper function with parameters. Everything mostly remains the same, like base case, traverse, going down. The logic will be changed either here, like we're updating, or whatever you return when you're processing the node. Any questions here? Yes. That's why some interviews, I don't think it's correct ask during the interview, remove the global function, because we all know that we are not writing production code, and you can mention this downsides of the global function. But I was on some interview where interviewer one insists do not use the global function. But with global function, in my opinion, code is more cleaner and it's easier to solve. So you have once you will solve more tree problem, you will see that sometimes is one function is not enough, as we did here. Just to introducing one function is not enough for recursion. Sometimes it will require you to introduce actual helper function, which will be your recursion function, which makes some computation inside. Either it will be updating the global function, or it will be updating something which is your extended your recursion function with the some like variables or the parameters. Is it clear? I believe it's not. But you can try to ask me some questions.
Actually, I don't have a question on the topic, but I was thinking that because now we're going into more hard and advanced topics in this LeetCode, I was wondering if you can just pace it down by, doing less, but so then we can, digest the information. I don't know if that works for you.
Yeah, that makes sense. Absolutely. I'm trying to make it less. Yeah.
Like maybe we can solve half of this in one session and half of this in the next one. I definitely have to rewatch this recording, especially the second half, to plan things again.
So I'm happy to stop here. It's actually 3 problems, just 3 problems, Moina. It just feels overwhelming. Before, when this was more trivial questions, you had homework with 5 and 6 problems, actually. And sometimes I was leaving this. Currently, yes, I'm keeping it very small and short.
Yeah.
Let's do one thing.
Yeah.
I'm not going to cover this one because it's BFS. I will include it because it's pure BFS. Let's focus this homework, and I will remove the 4th one. Let's just try to focus on solving this problem with recursion, because this is something which has helped you to be more comfortable. Just focus on 2 templates, which as I showed today. This is one template where recursion function doesn't need to be modified, and it's calling itself. And you have just introduced base case and to make some process here, processing somehow your nodes. And there is, I added some tweak, which is more advanced recursion function, which is actually including recursion function as a helper method, and it is has global, or it could be solved with the a parameter on the help function. So let's focus then on these 2 things. Ask Irene.
It's more just a point. For this to really sink in, we just need to go away and play with it. So you're saying there's 2 approaches when you're introducing a helper function. I suggest people just go away and play with both versions, because it's quite hard for you to get this over to us, Lilia, without us playing. It only really sinks in when you start coding it up and trying it for ourselves, I suspect.
Yes. And I think what I can post additionally on the Slack to make it more visual for the recursion. Yeah. Okay, folks. Then let's stop here. I will remove this binary tree site from the assignment. and it will require it just to solve this and this. This required a very straightforward template of the recursion to use. Also, look at the iterative solution, which is I posted on the whiteboard. And another one, it is just can be solved with recursion, because it could be solved with iterative approach, but it is a very complex one. And yeah, I will remove from the contest, manage contest challenges. Done. So, okay, folks, we are running over the time. If there is no other questions, have a good weekend.
So Lilia, just to confirm, that last one, you're going to add it for next week?
Yes.
Tree, right, lovely. Thank
Yeah,
you.
definitely. I won't remove probably from here. Still keep it, because once I will create a whiteboard for the next, I will probably move. But for now, just just keep it aside.
Thank you.
Thank you, folks. Yeah. Thank you. Folks, thank you so much for coming.
Thanks. Have a good weekend.
You
Have
too.
a great weekend.
Yeah.
Sorry, Anita, I'm going to remove you from the call.
Yeah.
Окей, good. Так, давай выключим рекординг.
Ага.
Стоп.